Hello everybody, this is Rudra Pradhan here. Welcome to Engineering Econometrics. Today we will continue with modeling diagnostics and that too autocorrelation problem. In the last lecture we have discussed this particular component. Basically it is the problem among the error terms. As we have already discussed in a kind of econometric modeling, we have dependent variable and we have independent variable explained and independent variable unexplained. So, autocorrelation is a game of unexplained independent variable, that too among the error terms. So, like we have discussed the issue of multicollinearity, which is the game of the relationship between independent variables explained, and here it is the similar kind of structure, but we like to establish here the relationship among the unexplained independent variable, that too with respect to error variables only. And in fact, we have discussed in details how we can derive this particular autocorrelations, and we have discussed various regions, various mechanisms through which you can detect the autocorrelation, and we have also discussed the kind of tolerance labels and the kind of consequence, and the thing which we like to discuss today is the solution part, and before that we can discuss a particular problem, and we like to check how the particular autocorrelation problem and what is the degree of involvement. There are lots of techniques through which we can actually get to know the degree of autocorrelation in a particular system. For instance, simply graphical plotting or simply correlating between two independent variables, we can get to know the involvement of autocorrelation problem in a kind of estimated model. But the standard techniques through which we can actually detect the process is called as Durbin Watson D statistic, that is otherwise called as a DWD statistics. Most of the statistical software and econometry softwares used to provide this particular statistic, and we have already discussed in details in the last lecture. And the usual structure is that if we start with like this, the particular structure is y equal to beta 0 beta 1 x 1 t plus u t, and then u t equal to rho u t minus 1 rho u t minus 1 plus b t. So, rho is the autocorrelation coefficient, and then rho is nothing but actually a correlation between u t and u t minus 1. So, this is what we have discussed in the last lecture. Now, if you connect with the Durbin Watson D statistics, then it is nothing but d equal to 2 into 1 minus rho. Of course, there is a mathematical procedure how to obtain this d component, but ultimately after this simplification you can get d equal to 2 into 1 minus rho, and rho is the autocorrelation coefficient. Since a autocorrelation coefficient lying between minus 1 to 1, so d will be ranging from 0 to 4. So, that means a rho will be varying from minus 1 to 1, and Durbin Watson D statistic will be ranging from 0 to 4. So, ideal range is for autocorrelation, and that too good modeling for any kind of decision making process where d must be equal to 2. So, that means technically if you have a rho equal to 0, then there is no autocorrelation, and in that context by default d equal to 2, and if rho not equal to 0, then it may have a negative value, it may have a positive value, and one extreme is minus 1, another extreme is plus 1. So, as a result, so DW statistic, the extreme ranges are 0 and 4 by putting rho equal to minus 1 and plus 1 respectively. So, ultimately we like to check what is the value of D in a kind of an estimated model, whether it is a ideal in nature or it is a kind of problematic in nature. So, we have given the confidence interval, and that means technically D must be ranging between 1.5 to 2.5. That is the acceptable kind of criteria through which you can go ahead with the modeling and the kind of decision making process. Otherwise, to getting the ideal value D equal to 2 where rho equal to 0 is very difficult one, and as a result it may be lying in between 1.5 to 2.5, and if it is exceeding less than 1.5 or more than say 2.5, then slowly it will be actually dangerous for any kind of modeling process. So, if it is crossing 2.5 or lesser than 1.5, in that case we need actually restructuring of the model. Then we will go for fresh estimations. Again we will have a estimated model. Then we will again follow the same procedure of checking the autocorrelation, and then we can compare the previous autocorrelation value and the later autocorrelation value, and we can actually move to the second models or second iterative process if that particular DW statistic will be lesser or in a kind of ideal range compared to the previous one. So, that is how it is a iterative process, and in fact it is a continuous process until unless you get a model which is free from autocorrelations or which must be in a kind of ideal range between 1.5 to 2.5. So, now in these lectures we like to highlight two things. We first solve a problems and like to know how to get this DW statistic through some kind of software, and then we like to check the solution part of this autocorrelation problems and other major issues relating to the autocorrelation problem. But it is a big virus. Until unless you take care this particular part, we should not use the estimated model for any kind of decision making process, and that to solve any kind of engineering problems. So, let us see how is this particular look. So, we have a problem here, and the problem is for a manufacturing company, and in the manufacturing company the process is actually they will have inputs process and they will go with kind of an output, and ultimately having output they will send it to the market for selling, and when there is a question of selling of their product in the market, then management come into the picture, and obviously they will have a different kind of planning or the kind of management, so that the sales should be at the highest level, and for that there are many factors, and the particular company has to take care all these factors in order to achieve their goals to increase these sales and then increase their production process. So, number of factors will be involved in this process, that to how to increase the sales of a particular company, starting with price of the particular product, and then the advertising expenditure, infrastructural availability, like so many factors will be there. So, you can go through theory of this particular problem, then find out what are the factors, main factors responsible for this particular product, and that too for that company, because sometimes factors varying from product to product and factors varying from company to company with a particular product. So, there are many different issues altogether there. So, what will you do? We will just have this particular data and check whether the particular factor is very effective for this sales forecasting. And one of the factor which can usually helpful for sales forecasting or production forecasting is the advertising expenditure. With the theoretical understanding is that, so if you put more and more advertising, then people will get to know about the product and about the value of this particular product, and then there is a high chance there will be more and more sales. So, that means technically the theoretical hypothesis is that more is the advertising expenditure, more is the kind of sales, and less is the kind of advertising expenditure, less is the kind of sales. So, we like to check whether this particular statement is true or false, and for that we are using a econometric modeling. And then we simply start with the modeling structure is that sales is a function of advertising expenditure, and they are linearly related to each other, and there is a positive relationship between the two, and as a result the beta coefficient should be positive, and that should be statistically also significant. So, having these problems for this company and the particular items like this side. So, we have actually sales value, and then we have sales value, and then we have actually advertising expenditure. Then we like to correlate and regress, get to know how is the particular. For this we will go to this problem set. So, same data set I have here actually loaded, and that too I will just increase the view. Okay. So, this is what the sales data, and first row belongs to sales data, second row belongs to advertising expenditure. We can solve this problem in any software, but I am now using the Excel software, and because I like to know how we can derive this Durbin Watson D statistics. So, this is obviously first and structure is that we like to regress sales with advertising expenditure. For that we can pick up the data analysis package, and since it is a regression, so just you click the regression, and then you can give first y range, that to starting with first item 153 to last item 209, and then give the input range, that is first item is 5.5, and that to continue with the last item will be 6.4, and that to both the variables have same samples, that is 20 data points, and both having actually some kind of fluctuations. As a result, both variables informations are reliable and consistent to regress the particular equation, and that to fit the model as per the particular problem is a concern. So, now giving the dependent variable range and independent variable range, now the software ready to operate and process, and that too can give you the kind of estimated output. But before that I like to highlight that autocorrelation is a problem. It may be it means the model may be bivariate, may be trivariate, may be multiple or multivariate. This problem will be always there. So, this is a genuine problem, and why I have highlighted this, because in the case of multicollinearity there should be actually a multiple independent variables, and then we can apply this particular structure. But here even if you have a two variable case y and single independent variable x, still we can derive a error component and create further error term to regress and then go ahead with the autocorrelations. Now, with this particular problem we will have this kind of structure. Let us put okay, and then we will have actually estimated output this way, and then here as usual the slope coefficient is coming positive and statistically significant, and as a result it is going in favor of our hypothesis. And what will we do? So, we like to check the level of autocorrelations. For that the process is not actually ready. That means technically we have estimated coefficient, standard errors, then t statistic, probability value, and then R square value, then adjusted R square value, f value, everything is actually in favor of our modeling. So, that means this data and this model is very much effective so far as SFT and GFT is concerned. So, now we will go to DGT part, where we will take care of the autocorrelation issue. In that case we can go to the sheet 1. So, here in the sheet 2, so the coefficient is actually minus 43.8, then 35.95. So, again, so what will you do? You will create here estimated sales. Let us say estimated sales, Okay. Now what is happening? So this is equal to simply a minus 43.8 minus 43.8. So that means technically we move to here minus 43.8. So this is equal to minus 43.8 plus 35.9 into x. Okay, this is 35.95 into x. So this will give you some kind of forecasted figure. Now what we can do, you just actually scroll it, you just scroll it, then you will get the kind of okay. So this is what the estimated output, and then after having the estimated output, what we can do, so we like to check the error component, then we will derive the error variable here. So error is the difference between the actual cells and the forecasted cell, that is the predicted cells, and this way. So you will get the error component. Okay, so this is what the error variable behaviors. Now this is what is called as actually UT. Okay, so next in the next instance you can create actually UT minus 1, and for that, so you just copy this particular variable. Okay, we can copy this particular variable. Okay, so this is all right. Okay. Second, I will just add it. Okay, this is all right. So now we can copy this particular variable, then we can just paste 1 point behind, and that too we can have with all right. This will give you, this is okay. So now this will be like this. Okay, so now this is UT minus 1, and then our autocorrelation coefficient will be autocorrelation coefficient will be in between actually. So the autocorrelation coefficient here it will be autocorrelation variable here will be covariance of UT upon UT minus 1 divided by variance of UT. So this is what the autocorrelation coefficient. So that means if you simplify, then it will give you something like summation. It is if you simplify, then it will give you some kind of the covariance between UT minus 1, that is nothing but ET minus 1 by sigma square ET. So it is better to come here and see the kind of structure. Okay, so all right. So let me come to this this particular problem. Okay, so this is what the kind of case. So now we have actually monthly data of 20 data points, 20 different months, then sales figures, then advertising expenditure, and this is the plotting, and that to know the link between sales and advertising expenditure. And after that we are looking for actually the Durbin Watson D statistics. So the estimated equation will be y hat equal to minus 43.80 and plus 35.9 x, which we have already highlighted here from the software. So that is the software result here, 43.8 and 39.5, and then we have the error component and the log of the error component. These are the typical inputs in this particular autocorrelation detection. So now, so the estimated equation is y equal to minus 43.8 and this one, and then coefficient is r square 0.83. So now with this actually we like to proceed for the autocorrelation check. That is why we have created actually the kind of error components, that to here the y head which we have already derived, and that to error component is this much which we have also derived. And then what we will do here, so we will create a log of the error terms, this row, and this is what the estimated equation, and this is how the error terms. Just now I have highlighted in the Excel sheet, and then we can create log of the error terms, and the Durbin Watson d statistic value will be actually, so the division between actually the square of this covariance and then the variance of this error terms. So now we have to find out the square of this difference and then square of the error terms, and then if you will divide, so you will get the kind of component of Durbin Watson and d statistics. So technically, so this is how the behavior. So we will see how is the kind of structure altogether. So ultimately the equation is like this, and this is what the Durbin Watson d statistic is testing. And what will you do here? So after getting this particular series, so you just divide this into this, so you can get the autocorrelation coefficient. So that means technically, so it is nothing but actually a summation et minus 1 whole square divided by summation et square. So that is what the Durbin Watson d statistics, and after this process you can have this value, and let us see what is that particular value from this equation, and for that you have to actually move further. Okay, so this is what the first of all the null hypothesis will be rho equal to 0 against rho not equal to 0, and then the critical value we will go for testing, because we have also Durbin Watson d statistic tables. So here we will calculate the Durbin Watson d value and then compare with tabulated value. If it will overtake this particular coefficient, then we can say that autocorrelation is present, and that too it is significant, and if it is significant, then it may not be used for the kind of model decisions or managing decision. So this is what the calculating mechanisms which I have already highlighted. So it is coming actually 0.85. So that means if you divide these two values, so it is coming 0.25, which is actually not exactly ideal, because for ideal we should have actually d value equal to 2, and again so we have kept the confidence interval 1.5 to say 2.5, and here it is actually less than to 1.5, that means close to 1, let us say 0.85 means close to 1, and that to positive autocorrelation, and as a result this particular value is not actually good for the modeling, and that too for any kind of decision making process. So the value itself indicates that there is a need of restructuring of the whole process, and go for the re-estimations, and again have the new estimated model, and then repeat the process till you get the d value within the range between 1.5 to 2.5. That is what the usual procedure, and then again accordingly we can go ahead, and means the whole process is actually iterative kind of things. Every times you can actually check and then see the kind of range. If there is a need of restructuring or re-estimation, go ahead with restructuring and re-estimations and repeat the process. Otherwise you can stop and go ahead with the prediction, forecasting, and the kind of decision making as per the requirement of the engineering problem. And Durbin Watson D statistic itself has some drawbacks. It may give some kind of inconclusive results, and it is not applicable when lag dependent variable is there, because we whatever technique which we have used till now with the intention that it's the dependent variable and independent variable only, that to explain. So, no lag involvement. Of course, after getting the error terms, we are connecting to the lag error terms, but the starting process is that dependent variable with the only explained independent variable without any lag involvement. That is what is technically called as the endogeneity issue, but in a real life scenario the involvement of lag variable is also needed because of endogeneity check. Then in that case, so instead of using Durbin Watson D statistic, we will use Durbin Watson H statistics. So, it will be having like this. So, I will give you the Durbin Watson H statistic structures. This is what actually Durbin Watson D statistic structure. So, instead of D, we call it say H, and then so it is simply actually first get the dw value. So, 1 minus dw by 2, then square root of n by 1 minus n sigma square estimated. So, it will give you some kind of figures like Durbin Watson D statistic. So, we will use now Durbin Watson S statistics to represent the accuracy of the models, and then use the model for the kind of decision making. So, this is actually normal procedure through which you can actually proceed and move, and besides we have lots of other tests like BG test, where we are regressing first YT with independent variables, that is explained, and then we derive error terms and then connect error term with log of the error terms, and then check the significant means just you have to derive the coefficients and check whether the coefficients are statistically significant or not. If they are statistically significant, then there is autocorrelation, and if they are not statistically significant, then there is no autocorrelation. So, this is how the process is all about. And then if you are just regressing UT upon log of the UT, like UT minus 1, UT minus 2 and so on. So, in that case, so we can use actually Lagrangian multiplier test, where the value of R square can be tested and compare with the tabulated value, and the final conclusion is that whether the particular H value is statistically significant, or the means that is the Durbin Watson value will be statistically significant or not, and if it is statistically significant, then the particular problem is problematic, and we have to find out the solutions that to either restructuring of the entire model or the entire process, or simply change the functional form and then go for re-estimations, or change the variable structure again go for re-estimation. So, that means we have plenty of options so far as a solution to the Durbin Watson means autocorrelation is concerned. The best solution mechanisms are go for data transformation, increase the sample size, change the functional form, add different variable. Sometimes due to misspecification of the model, so we can have some kind of autocorrelation problem. So, we can use trial and error method by increasing sample size, decreasing sample size, change the functional form, addition of new variables, then removal of the existing variables. So, after doing all these kind of cross check, so you will find the ultimately means the estimated model which is free from autocorrelation. Even if there is autocorrelation, but it will be in a ideal range, that too in between 1.5 to 2.5. So, this is how the process, and this is the similar kind of problems through which you actually means same problems can be connected with Durbin Watson S statistic instead of D statistics. So, that means we are regressing sales with advertising expenditure, just you add sales of the previous years, that's the kind of log dependent variables. If you enter to the model, then the model will become a trivariate, and in that case you can use Durbin Watson S statistics instead of Durbin Watson D statistic, and then check the accuracy of the model. So, this is the usual procedure, but every time the requirement is that you have to see whether the model is free from all kind of diagnostics, and then come to a kind of conclusion that yes, this is the model through which you can go for decision making process. Ultimately, here rho is the kind of component which can check the kind of autocorrelation behavior. So, far as the solution is concerned, so we have two different instances. First, when rho is known and when rho is unknown. So, now looking for the kind of structure, we have to first estimate, then first you go by simple estimation by dependent and independent variable, then get the error component, and again estimate the error component with its lag component, then you get to know the rho value, and again so the rho value can be used for the kind of autocorrelation solutions. So, that means when rho value is known, so just to multiply the rho value and again restructure the entire process, I am sure the autocorrelation problem can be solved some extent. That means like this way, here after multiplying rho value, so you will get actually some kind of additional tricks. So, now just the first equation and the second equation, if you simplify, and you will get a new equation, and that new equation if you go by estimation, it will be absolutely free from the autocorrelation problem. So, that is what the model is all about, and when P is known, so we will follow the particular process. Likewise, there are many different mechanisms through which you can actually solve the autocorrelation problem. So, ultimately the summation is that while solving a particular engineering problem through engineering econometrics, so you must have a sufficient theory, you must know the variables through which the theory can represent, then you can specify the models, have the data, and develop a model, then estimate the model, have the estimated parameters, then check the parameters are statistically significant, the fitness of the model is good enough, then you go through all the diagnostics starting with the multicollinearity, then autocorrelation, then at end of the day we should have a estimated model which is actually passes through specification test, GFT, and then no multicollinearity problem if it is multiple regression case, and no autocorrelation. Then finally you can use this model for the kind of management decision, and that to solve the engineering problem. And till now we have discussed up to the autocorrelation, but there are lots of other diagnostic which you need to take care before you declare that the model is fit for the decision making or the kind of solving the engineering problem. And in the next class we will discuss this other diagnostics, and in the meantime we will stop here, and thank you very much. Have a nice day.